Hi, this is Kevin Dowling. I'm with Philips Solid State Lighting in Burlington, Massachusetts. I'm the head of innovation, but my industrial roles include chairman of the IES subcommittee on solid state lighting, as well as the NEMA subcommittee on solid state lighting. And these activities are mostly related to standards, which we'll also cover here today. What I hope to impart to you today is the advent of LEDs as an alternative to traditional lighting sources. Wherein LEDs have improved markedly, and we'll see exactly how much they've improved over the past several decades, so that they can now be considered for general illumination. This really wasn't possible until just recently, but we'll take a look at applications, both current, past, and future applications of LEDs for lighting. And in this talk, I hope to show you a variety of applications, as well as how LEDs work, various trends that are marching forward with LEDs, and quite a few applications, as I say, we'll have a chance to see as well. And if we go back in time, most of the different applications we see in our lives today have all made a transition from analog to digital. If you look at the vacuum tube, of course, that became the transistor. And long-playing records became CDs, which have even further transitioned to non-rotating media in the form of MP3 files. Film cameras have become imaging sensors. Phones, of course, have not only become digital, but also wireless, and a variety of other applications. There are many of these. One of the most interesting points about this is that lighting has not made that transition, and lighting really is the last refuge of analog. And we believe that that's in the midst of a transition too, due to light-emitting diodes, or LEDs as they're called. And so we're going to see over time how much this has changed. For LEDs themselves, they haven't been around that long, but they've been around longer than many people think. In the early 60s is when they were first really discovered. A gentleman in the upper right here named Nick Holonyak was at General Electric's research lab in Syracuse, created the first visible light LED. The brightness of that was quite low. It's estimated it's around 1,000th of a lumen. You could only see it in a laboratory under dark conditions. But of course, as research continued, they continue to improve quite rapidly. Now, Dr. Holonyak, who was at General Electric for some time, actually quit General Electric, and in fact, General Electric shut down the research activities in this area, seeing no immediate commercialization potential for the LED. Dr. Holonyak went to the University of Illinois, where, in fact, his contributions to LEDs probably were even more considerable than even creating the device itself. Many of the students have gone on to become leading figures in solid-state physics and the creation of new LED technologies. By the mid-1960s, the late 1960s, a couple of companies, including Hewlett-Packard and Monsanto, had taken LEDs and tried to continue to improve them. And they were looking at very specific applications. Hewlett-Packard was looking for a way to have indicators and displays to replace the old analog instruments that they had currently at that time. They continued to improve the LEDs, and then through the 70s and 80s, more colors, that is further up the visible spectrum, from reds up to ambers to greens, became possible, and some of the first real widespread applications of LEDs became possible as well, and this included watches and calculators. The one thing to point out in these applications, they were rather transitional. Both watches and calculators used LEDs for a relatively short time. The displays were power hungry. They were also rather dim, and in many cases required you to shroud the devices in order to see them, and in some cases, such as calculators, early Texas Instrument calculators, for example, that were based on LEDs, had hoods built into them so that you could, in fact, see them even in room light. The lumen output, that is the light output, continued to climb, but if you remember, and looking back here, that to go from 1,000th of a lumen to 100th of a lumen to 1/10 of a lumen is an order of magnitude, factors of 10, but that the ability to use this for a light source was still quite small. You really could not use this to light your way at this point. Through the 80s and 90s, these devices continued to improve, and you had quite bright systems, but the missing link was really the blue LED. And the gentleman in the lower right was Suji Nakamura, was with Nichia Chemical, which was a manufacturer of phosphors at the time, but became interested in LEDs. Dr. Nakamura actually took a very long look at a material that most people had discarded as a potential for high brightness LEDs, and made it work. It was a tremendous effort. He and his team created high brightness blue LEDs, high brightness greens using a material called GaN, or gallium nitride. And by the late 1990s, you had single LED packages producing light in excess of a single lumen. And at that point, people began to really take notice because it was bright enough to make you blink and could be used for a variety of high brightness indicators as well. The other thing I'd point out about blue is that it was the missing piece of the triumvirate of red, green, and blue, which in light are the primary colors. So the combination of red, green, and blue LEDs finally meant it was possible to create, for example, white light, or to have color mixing capabilities for LED systems. The blue LED also enabled the white LED, and as we'll see in a subsequent slide, the blue LED could be used in conjunction with a phosphor in order to create a broadband white light emission. All white LEDs are in fact blue LEDs inside. By the year 2000, the output of these devices had increased such that the packages, in some cases multi-chip devices, were able to put out over 10 up to 100 lumens in a single package. And by 2005 and currently, we're seeing multi-chip packages producing in excess of 1,000 lumens each, and at this point can be considered for use in general illumination. This is a big step and quite a bit of work. Now, at its most fundamental, the LED is a semiconductor device. In fact, more accurately, it's a compound semiconductor device that converts electrical energy directly into light. And that light output is a discrete color. LEDs only produce a single color. The dye itself can only produce color of a certain narrow spectrum within the visible spectrum, and that can be used in combination with others in order to create other colors or broader colors. These devices are made from compound materials. If you take certain elements, the columns of the periodic table, these compound semiconductors create devices that can then be used to efficiently turn electrons into light. It's essentially a combination of electrons and holes that release energy in the form of photons, and that is visible light. Now, the factories that these are made in also differ immensely from traditional lighting factories in that the devices are made in factories that are much more akin to computer chip factories than they are traditional lighting factories. A traditional lighting factory, in many cases, will actually take raw materials such as sand, turn that into a molten river of glass, and then those are turned into lamps and so forth. Within the LED factories, there are actually devices located in clean rooms that you need to wear bunny suits in that completely close you and prevent you from bringing dirt into the facility and other contaminants. And these factories are very quiet. The machines are very quiet as well. And it's basically a mixing of chemicals and compounds and dopants that are put into substrates and then compiled up like almost like layer cakes. And as I mentioned, white LEDs are actually blue LEDs plus phosphor, and that's a subsequent operation once they leave the chip fab. The diagram in the lower left shows the substrate on the bottom and various layers on top of that, the positive or P-type and N-type layers through which the electrons progress, combine with holes, release energy, and in some cases, as shown in this diagram, there's an additional phosphor coating that is used to down-convert the light into broadband white light illumination. In the lower right is a traditional looking LED. The small bullet-shaped device is often termed a 5mm LED, or in some cases a T1 3/4 using the traditional lamp nomenclature for describing the diameter of lamps in 1/8 of an inch. In this case, the lens itself is made of epoxy. More recent devices use silicone. This forms an encapsulation around the LED, which consists of not just the dye itself, but the wire bond, the reflector cup, and so forth. All of these combine to produce a complete package, and electricity can be put into the leads and go through the wire bond into the LED dye and then emit light. This is a very traditional LED. In fact, most LEDs today are still of this form. This really took the place of a traditional lamp source called a grain of wheat bulb of about the same size. But many package shapes are now available, especially in high brightness LEDs. The high power packages are much different. Now, if we take a step back and look at the lighting industry, and we can see a very large and old industry. Lighting, although the numbers vary from market study to market study, ranges from around $70 to $100 billion a year globally, and that includes lamps and luminaires, fixtures, and so forth. Lighting is also over about 20% of electricity use. That generally holds worldwide. It varies according to country and region, but it's roughly 1/5 of all electricity use. In the U.S., that energy costs about $40 billion a year, so there's a significant amount of cost associated with running these devices above and beyond the cost of the devices themselves. And the Department of Energy in another study has shown that LED-based lighting could reduce lighting energy by half by the year 2025 if it's adopted. And savings over that same time period from around 2000 to 2020 could eliminate the need for a large number of large power plants and save well over $100 billion in energy costs. So there's great interest in LEDs as efficient light sources for the purposes of saving energy and saving costs. And the Department of Energy is in strong support of this for obvious reasons. Now here's one example. This is a traffic light that is using LEDs. This has actually become fairly prevalent. Probably more than 40 to 50% of traffic lights nationwide in the U.S. are now transitioning to LEDs, and the rest probably will over time as well. And some of the reasons for that, for a municipality, the cost to run an incandescent traffic light is about $16 per year just in energy. And even though in most cases the one lamp is on at any one time, the total cost of this running 24/7 over 365 days a year can add up. The cost to run an equivalent LED traffic light is about 1/8 of that, or $2 a year. And the DOE estimates that replacing U.S. traffic signals with LEDs, replacing incandescent sources, could save about $200 million a year in energy costs. And this doesn't even include the maintenance costs, which happen on a pre-scheduled basis. These devices, the social costs of having lamps out in a traffic light are quite high, so there is a scheduling that's done in order to replace these before they burn out so that they don't, you rarely see them burned out in actual applications. Now, LEDs have been used for many types of applications over the years, from monochrome indicators used in traffic lights and automotive and exit signs, to portable appliances. Your cell phone and PDAs most likely have LED backlights. Signage is becoming quite common, including direct view displays and video screens now being comprised of large numbers of LEDs. If you think about Times Square, the NASDAQ sign shown in the lower right of the slide is an example of a very large-scale video screen using millions of LEDs. This is quite common now for scoreboards and football stadiums and baseball parks and so forth to have these types of LED-based video displays. For general displays, such as the LCD display you may be watching this very webinar on, it's becoming quite common now to have LED backlights for those instead of the cold cathode, both to save energy, increase reliability, and also decrease the size of the unit. So there's more and more applications. Generally, in color applications today, LEDs are extraordinarily efficient because there's no need to subtract out most of the light to create a specific color. So for most color applications, LEDs have become the dominant means of creating color with light. Other emerging applications, especially in transportation, include marine, auto, and aviation. Many of the indicators and lights used in those forms are switching to LEDs. And many lighting niches today, accent and decorative lighting, effects lighting, and so forth, have become quite common using LEDs. And in the near future, we believe that general illumination, both as cost comes down, performance continues to improve, that we'll see more and more LEDs used in these types of applications as well. Now, if we take a look at conventional lighting sources, which many of you are very likely familiar with, from incandescent to halogen to fluorescent to gas discharge sources such as neon that are primarily used in signage, we understand the limitations and the efficacies and so forth associated with those. But what many people may not know are the benefits of solid-state lighting over some of these sources, and we'll take a detailed look at some of these. But some of those include an ultra-long source life, and I guess the real question is, well, what is that life and how long? And we'll take a closer look at that. Low power consumption, which comes about from being an efficient light source, and low maintenance, which is also related to that. No moving parts may seem like a rather odd comparison, but when creating colored systems, very often there's moving parts such as filter wheels and so forth that are used in order to create and change colors of light, especially in theatrical applications. Very good vibration resistance. If you remember back to the slide showing the overall schematic of an LED, the wire bond and the LED die are fully encapsulated in the epoxy or silicone that's used to hold it all together, and thus the device is very resistant to vibration and shaking. Now, the next two attributes, no UV and a cool beam of light, are both related to the fact that the LED light is right smack in the middle of the visible spectrum. There is no ultraviolet, which is beyond the blue, and no infrared, which is beyond the red parts of the visible spectrum. What this does not mean, however, that although you have a cool beam of light, an LED still produces heat. It is not perfectly efficient. And as a result, although it doesn't radiate any heat, it will conduct heat, and very often that's a critical aspect to the design and construction of LED lighting systems. Another attribute is that they're digitally controllable. The electronic devices that are diodes and LEDs are easily interfaced to traditional control processors and switches, transistors, and so forth. And this makes it very, very easy to control LEDs. Finally, and one of many other attributes for LEDs, they have very, very fast response. There are certain types of LEDs, infrared LEDs in fact, that are used for communication. Your television remote, for example, most likely has an infrared LED that is turned on and off very quickly in order to communicate with your stereo or entertainment center or television. As a result, LEDs can turn on and off very quickly and don't have the typical thermal lag associated with incandescent and halogen sources. You can often see this effect if you look at the brake lights of cars that have switched to LED lights rather than having the incandescent sources, which take on the order of 100 milliseconds to switch and change. That might not seem like a lot, 100 milliseconds being a tenth of a second, but if you're traveling at 60 miles an hour and respond to a light, the brake light of a car in front of you, 100 milliseconds at 60 miles an hour is about 10 to 12 feet, 3 to 4 meters, and so that's substantial at those speeds. So as you can see, there are many types of benefits and attributes to LEDs over traditional sources. Now, one of the aspects I had mentioned was that of lifetime. In traditional lighting, the lifetime is defined as the average time to failure, that is, complete failure to darkness. The problem is the mechanisms by which traditional lamps fail is often that of filament breach, that is, the filament actually breaks. And you often see this when a light bulb fails. It fails when you turn it on. The thermal shock from going from room temperature to a very high temperature will cause an aged filament to finally breach or break, and you get that bright flash of light. With LEDs, you don't have a filament, so the mechanism for failure is much different. In fact, the mechanism takes a very long time. It's termed lumen depreciation, and that is the light drops in output over a very long period of time. So the difficulty is, how do you define failure if it's still emitting light? Well, the industry and customers within the industry have come to a consensus that if your light output is down around 30% from initial light output, that could be defined as your lifetime. And 30% down from initial may seem like a lot, but the eye is very nonlinear in its response to light. It often takes quite a while to even notice that lights are dimmed down significantly. And it's thought that, or suggested that in the industry, that 30% down for general lighting is acceptable, and that perhaps even down to 50% for less critical applications such as accent or decorative lighting, where you still have a sufficient amount of light, but it's not tied into safety considerations and maintaining certain lighting levels. Then fluorescence, for example, and incandescents also have lumen depreciation, but their lifetimes are so much shorter that it's not really noticeable. And fluorescents, in fact, can be down 25% over their shorter lifetimes. Incandescents down 15 to 20% over their appreciably shorter lifetimes. But the real question is then, what is the lifetime of an LED? Well, the real answer is your mileage may vary. That's not meant to be a glib answer. It really is the case that it depends on the environment. It depends on the engineering of the fixture around the LED. But predicted LED source life is between 50 to 100,000 hours based on maintaining temperatures at prescribed levels. And that's quite typical for high flux or high brightness LEDs. So lifetime is significant. 50,000 hours is one example, is over 6 years of time running 24 hours a day, 7 days a week. So it's a significant amount of time, and no matter how you measure that. There are 3 graphs here that tell a very compelling story. The first is related to luminous efficacy, that is the amount of light out for power in. And as shown in this graph, the orange line showing the incandescent line is pretty much flatlined. There's been very little change or improvement in the light output of incandescent sources over the past decades. In fact, almost over the past century. The initial improvements started by Edison and Swan and others culminated in a very reliable device by the early 1900s. But the overall efficacy, that is the lumens out per power in, has remained steady at around 10 to 12 lumens per watt. The result is that there really hasn't been a lot of improvement except as new technologies get introduced. So for example, halogen, which showed the introduction of halogen gases into the lamp, that allowed the filament to recombine and further improve brightness and output, such that the halogen lamp was an improvement over the incandescent, as was the IR halogen much later. But the fluorescent lamp was generally much more efficient and over time continued to improve rapidly, both in quality of the light as well as the efficacy of the light. And the best of breed sources today in the fluorescent technology are around 90 lumens per watt. Generally for compact fluorescents, those pigtail-shaped lamps that sort of look like soft ice cream on a cone are really in the order of around 50 lumens per watt. Now remember that I'm talking primarily about source efficacy. Once you put these devices into fixtures or luminaires, then it's a different story. Much of the light can be lost in those devices because of shading and reflections and mirroring and diffusion of that light within the systems. LEDs have a different story. They came much later. They are the new kid on the block and then continue to improve quite rapidly through the late 80s and early 90s, and even today are improving as people continue to invest a great deal into LEDs to improving their overall light output and improve their overall efficacy. And we see them today eclipsing incandescent and halogen lights in terms of efficacy and fast approaching fluorescence even in a steady state basis. And so we continue to see rapid improvements. This is not a snapshot. This is really a moving target. In the second graph, these are actually very steep curves. The vertical axis is actually a log scale, which means that goes up by factors of 10. So if we were to plot this in a more traditional linear scale, these would be extraordinarily steep curves. The use of the log scale allows us to draw straight lines to show exponential trends. And there are two trends shown here. The one leading from the lower left to the upper right shows an improvement in the overall performance per package that is substantial. It's about 35% per year, year over year for several decades. The compound annual growth rate of the performance of an LED package is about 35% per year. If you think about that in investment terms, if you had a return on your money of that much, you're right up there with Warren Buffett in terms of return on investment. Simultaneously, with the improvement in performance, there's also a decrease in cost that is on the order of 20% per year. And the combination of these two trends really reveals an astonishing change that is akin to Moore's law in computing. Moore's law in computing says that the number of transistors on a chip will double every 18 to 24 months. But it also has ramifications for speed and cost and performance and so forth. That's the same thing here. This is also a semiconductor-based technology. And about every 18 to 24 months, you're seeing a rough doubling of price and performance of LEDs. And that trend has continued, in some cases even accelerated. Now, if we take those trends, and we have no reason to believe that these will not continue into the future, all results indicate that, in fact, in some cases, that it's accelerating. And we take into account lifetime, source efficacy, energy costs, replacement costs, and labor costs, we can get a true cost of light. In this formulation, you can find this in the IES handbook in a chapter on lighting economics, is termed the cost of light. It takes into account not just the upfront cost, which is the cost that you pay for a lamp. For example, if you go to a hardware store or a supermarket or a do-it-yourself warehouse, the cost of a lamp is traditionally quite low, maybe a quarter for an incandescent lamp source. But that's not the real cost of light. The real cost of light is not only that upfront cost, but the cost of energy required to drive it over its lifetime. And if we take all of these factors into account, we see that the cost of solid-state lighting has been dropping rapidly over the past decade. And we've come to a point where we've already eclipsed incandescent and halogen for some applications today, and fast approaching fluorescent territory for, at least on an economic basis, where LEDs can be considered as replacement technologies. Now, in order to show that, there are a couple of installations I can show here. On the right-hand side of your screen, or the graph, is shown the Hard Rock Hotel and Casino in Las Vegas. And they replaced 1,000-watt metal halide systems that were circling the exterior of the building from ground level, and replaced those with LED systems. And the Hard Rock Hotel and Casino estimated they were saving on the order of over $40,000 per year on energy and maintenance with the LED systems, where the cost of energy was reduced substantially and the cost of maintenance even more so in some cases. And so if we take all of these different costs into account, it shows some substantial savings for many applications. In the bottom right is shown Boathouse Row in Philadelphia, where the row houses that are used to store the various sculls and rowboats within the facilities there are all now lined with LED lights. And they estimated the annual cost savings to be close to $60,000 a year, again, both for energy and maintenance. So the cost of light criteria is not just the upfront cost, the energy cost, consumption, labor, lifetime, and light output, and so forth, and can add up to be very significant. And those trends will only improve. Now, if we look at a complete LED system, you have to remember that an LED system is not just the LEDs. LEDs may be one of the more important aspects of an LED lighting system, but there's power conversion and management. There are drivers, controls, and sensing. There's thermal management of these devices, which is critical to the lifetime of these systems. And then additionally, once the electricity is converted into light or photons, there's mixing and diffusion of that light and optical extraction of that light. We really want to leave no photon left behind. The system has to be efficient as a system, as an integrated unit, not just having good quality LEDs. And so the engineering of such systems is extremely important in this conversion process, as well as being reliable as a complete system. And if we look at today, there are a wide variety of complete lighting systems available using LEDs, ranging from interior and exterior fixtures, many of which are shown here, to accent and decorative lighting, including some direct replacement lamps, such as the MR16. There are Edison lamp types available as well, and people are working on many, many more. So all of these devices are pretty widely available today for many, many applications. Effects-based lighting, where people want to do very interesting things with large numbers of lights, is also very easy due to the digital controlling nature of LEDs. And now general white light illumination systems are also becoming available. And you can see in this slide that here are several examples of white light LED systems based on LEDs. With the addition of some interesting attributes, the ability to adjust the color temperature, for example, by using a mixture of warm white and cool white LEDs. And by controlling the intensity of the output of these LEDs, you can then create different color temperatures or colors of white light. And then there are also, of course, a fixed color temperature, which will allow the designer, the specifier, to select a particular LED color temperature and use that in their application. And here's an example of the ability of LEDs to produce different colors. And this should be a very nice attribute for designers to be able to select the color they want. There's already certainly expectations when you select paints, even if you choose the color white for a paint. There are many, many shades of white to choose from. And that also holds true for carpets and other surface materials. Well, why not have a choice in white light? You have a limited choice today in traditional lighting, but with LED systems, you may have the choice, much wider and broader choice. But not only that, but the ability to change that at will. So you can have an LED system, for example, that follows daylight. During the course of a day, the color temperature of the sky and the sun changes, and it would be quite easy to have an LED system do the same thing. And here you can see the effects of color temperature difference on food. In this example, from left to right, 3,000 Kelvin color temperature, 3,500 Kelvin, and 6,500 Kelvin. Now, the one on the right-hand side, the 6,500 Kelvin, is a very cool color temperature. I should also point out the irony between the Kelvin temperature, the color temperature, and what we would normally call cool colors and warm colors. They're actually inverse. So a very low color temperature is actually very warm, and the converse is true for the high color temperatures. But on the right-hand side here, you can see the 6,500 Kelvin has a very bluish cast to it. It makes the food look almost inedible. In the middle, it's a little more well-suited. It's okay, but clearly the warmer color temperatures down to 3,000 Kelvin are much more much better suited for the display of lighting for, in this case, chocolates. But it's very true that for all types of merchandise, from jewelry to fabrics to food, that the choice of color temperature is extremely important, and people pay a great deal of attention to lighting in specialty retail stores and supermarkets for precisely this reason. Now, we've seen some very good trends in LED lighting. We're starting to see increased awareness by the end users in the specification community, and increased specification of these systems as awareness continues to grow and experience continues to grow in using these systems, and as a result, increased market growth in LED lighting. These are all good trends. However, there are also bad trends, and these are things that can probably hurt the industry and hurt the specification of LED systems. And that is, the specification of these systems itself can be quite misleading, wherein the numbers that are bandied about are often at a minimum disingenuous, and in some cases much worse than that. So there's a real danger from hyperbole within the industry of overselling this, where this is a case where actually I heard someone at a lighting show several years ago talk about LEDs using the terms uses almost no energy and lasts forever. Neither are true. They do use energy and they don't last forever. And nothing will kill an industry faster than unmet expectations. There's a real need to set the stage for realistic expectations of a very good technology. The performance descriptions and specifications must be realistic and factual, and the costs must be complete in order to describe and specify these systems. There's another example where the LED companies, in many cases, are announcing wonderful efficacy levels for these devices, 86 lumens per watt, for example, or 100 lumens per watt, up to 131, 116, 150 lumen per watt white LED lamps. These are actual headlines, and they date over the past several years. Now, these are all true, except that they aren't realistic. These numbers are actually for pulsed measurements, that is, very rapid measurements at room temperature. So you end up with, let's say, 150 lumens per watt for 25 milliseconds at 25 C, sometimes termed the 25-25 test. This is fine if you're doing a pulse measurement to check the light output or the efficacy at the end of a manufacturing line, but do not indicate the efficacy that you have in your application, a real lighting application. Because this device has to be put into a package, that package has to be put onto a board, that board has to go into a housing, and there are losses all along the way, to the point where 150 lumens per watt may be reduced to less than half of that when all is said and done under steady state operating conditions. And so the LED companies are not necessarily being disingenuous about these numbers. These are actual measured numbers, but it's not clear that the standards are in place so that they're equivalent in an apples-to-apples comparison, and nor are they clear about where these numbers came from and exactly how they were measured. And so there needs to be some standards in place, and so many types of standards are now being proposed, and we'll talk a little bit about that in a second. In terms of the output, the sum of the parts does not equal the whole either. In some cases, you'll see spec sheets for LED systems where they use the nominal output of the LEDs, sum that up, and assume that that's the total light output. That is often not the case because of thermal considerations, so that you end up with an LED, for example, that can produce, say, 100 lumens. Add three of them together, you think you get 300 lumens. Well, you don't. You have inner reflections, you have thermal considerations, and other things that will reduce the overall light output to, in some cases, well below that of the sum of the nominal light output. Additionally, in this case, we're showing a fixture that was sent around to a number of laboratories in the U.S., all the top photometry laboratories of the big lamp manufacturers, as well as NIST and others, showing that the output of the device will drop over time as the device heats up. This is an LED fixture with a number of LEDs in it, wherein over a 2-hour period of time, the light output dropped from around 500 lumens to around 430 lumens, around a 10 to 15% drop in the output over that 2-hour period. At the end of that 2-hour period, that's a realistic number because that's what you would expect to see. But very clearly in the very early part of the cycle, it's much higher. And additionally, the Department of Energy has been doing several rounds of testing to show manufacturers that things need to change. The efficacy is shown in the left-hand column for each of the different products is shown in the highlighted column, the third column from the left, as being quite different. Whereas, for example, take a look at the downlight in the first row, actually the second row under the titles. that shows a 40 lumen per watt published number and under 13 lumen per watt for total luminaire efficacy. These are published numbers versus actual measured numbers. These are substantial, and what this says is that we need standards in place in order to accurately describe what these numbers are. We need those standards as soon as possible so that we have a uniform language and definitions, uniform test methods, and laboratory accreditation to show that. And quite a few people are involved in that, everyone from the IES, NEMA, Quorum, Next Generation Lighting Industry Alliance, the Department of Energy, and so forth. All are heavily involved in the standards process to create standards around safety, performance, and later architecture and form, perhaps new lamp types, as opposed to simply reusing old lamp types because of substantial improvements and by creating new lamp form factors around LEDs. On the safety standards side, there are 8750 at UL is in development. A standards technical panel, or STP, has been established, and there's quite a bit of work going on in this area. For the performance standards activities, there are about 7 or 8 different standards that are being worked on very actively right now: chromaticity, luminous flux, lumen depreciation, definitions, safety, drivers, and color quality, and so forth. So all of these are being worked on very actively, and it's hoped by early 2008 that some of these standards will be in place for Energy Star guidelines, which are coming online as well. In fact, if we look at color rendering in particular as a metric, we find that LEDs, in fact, have pointed out some substantial deficiencies in color rendering index, such that a new color quality index is being proposed that will fix a number of these deficiencies. If we look at CRI, it uses an obsolete color space. The original samples are relatively low saturation. The adaptation formula used for the calculation is also well out of date. It does very poorly in the red region, so a number of updates are being proposed. And in fact, just as a couple of examples here, some CRI numbers are really not equivalent. All of these CRI spectral power distributions shown here are 100, and you can see, at least visually and graphically, they're substantially different because they're all referenced to different lamp sources or different reference sources. And so in some cases, CRI can be quite misleading. An incandescent source, as one example, is almost by definition, since it's on the black body curve, incandescent sources have CRIs of 100. But that does not mean you render all colors well. As one example, try matching dark navy blue and black socks under lower medium luminance incandescent lamps. It's very difficult, if not impossible, because there's very little blue in an incandescent spectrum. This is just one example of why CRI does not mean it has perfect color fidelity and is a very good, not a very good reference for all types of colors. If we look at traditional lamp systems, there are a wide variety of infrastructure around lamps today that include transformers and power supplies, traditional controls, modular sockets, and lamp form factors. We believe that over time that LEDs will have their own versions of these, digital ballasts, for example, or power supplies as we might call them, control networks, modular sockets, and new types of lamp modules. And if we look at new form factors, here's a sketch or representation of one possibility, the ability to snap it in and replace it. So if it does fail for any reason, it can be easily replaced. Now, there's also quite a bit of activity around regulations and compliance associated with LED systems, and in California specifically, which has been on the forefront of many of these activities related to energy, Title 24 is California's energy efficiency standards for both residential and non-residential buildings. Today, as of this date, currently using the 2005 standards, but in 2008, we'll see a new version of this as well. The primary means for reducing energy use is to limit lighting power in a building, and that's what Title 24 does. The main reason for this is a California-focused graph. The pie chart shows the largest segment of electrical use is indoor lighting. 1/3 of all electrical consumption in California is related to lighting. So there's a gigantic incentive to reduce energy use, and Title 24 addresses this specifically. It does it through a means of looking at different allowed lighting power methods, which are various methods for calculating power use, ranging from single functions to areas to very specific tailored methods to general performance approach using particular programs and software to calculate that. But for lighting in general, minimum features for lighting include time switches, occupancy sensing, automatic daylighting control, photosensors, and other types of control devices. And you have factors that allow you to change and reduce your power load by using these types of control features. So Title 24 in many cases prescribes very specific power levels, typically today at 1 watt per square foot or less for lighting. Another area that has come under a great deal of interest is that of sustainability and a variety of other areas around that. And LEED, which is a lighting efficiency activity from the U.S. Green Building Council, is one such means to do that. And through LEED, you're able to accrue a number of points related to a certain level of sustainability and so forth within a building facility. Architects specifically are looking at this very closely, and in general, architects are looking at ways to improve the number of LEED points to be able to achieve certain LEED levels, gold, silver, platinum, and so forth. And LEED, as one component of that, does have lighting, which enables you to have several points as part of your accreditation for your building. Another aspect is Energy Star, which is a U.S. program to promote energy-efficient products. There is an LED lighting version in the works. Final releases have been made available, and it is likely to be in place by early 2008. And Energy Star specifically has, at least in this current version, 2 categories, one of very specific niche applications with very particular power and efficacy levels, as well as color rendering of certain levels, which is currently being used until such new indexes are made and used. Category B is generally efficacy-based performance, which is how much light for how much power, and devices can be evaluated in both categories. The criteria used for Energy Star include light output or luminous flux, power and power factor, efficacy, lifetime, CRI, and even the distribution of light. So there's quite a bit of work going on, and all of the standards required in order to have Energy Star in place. As I've already pointed out, CRI really is one that we're going to continue to address. In summary, if we look at the various activities around this, there are many tracking and supportive legislation activities. We're pushing hard in Energy Star and standards, and many supporting materials already as well. Our showcase, this is probably the most fun part, I think, for you folks listening in that we can look at some real-world lighting applications of LEDs today. There are many of them. There are tens of thousands of LED installations worldwide right now, probably numbering in the hundreds of thousands very, very soon. These include such landmarks as Hollywood Bowl, where the traditional lighting sources have been replaced entirely with LEDs, allowing for a wide variety of color effects. In Las Vegas, of course, there are many LEDs, not just in the signs and within the casinos themselves, but for some very large landmark projects that include the Lake of Dreams at the Wynn Las Vegas. This is a lake, a water lake, of course, with about 4,000 fixtures immersed in the lake itself, pointed upward. Several large compressors are used to infuse the lake with air bubbles, which then act as a diffusing medium within the lake to scatter the light. So you don't get the light bright effect. You're not seeing the direct LEDs. You're not able to directly view the fixtures. And so you can create these many wonderful patterns across the lake, and in essence use the lake as a display. Many retail applications, some of which include the well-known flagship toy store in New York, F.A.R. Schwartz, where the entire ceiling of the facility is only lit with LEDs. There are over 30,000 controllable nodes, which represents 90,000 LEDs that allow bitmaps and graphics and other imagery across the entire facility. Other include many retail outlets, such as the Lacoste boutique here, where the colored lighting is based on LEDs and used to accent the merchandising areas of the store. Here's an example of jewelry merchandising, Cartier in Paris, and many hospitality applications as well. It includes many hotels, such as the Bryant Park Hotel shown here, where a small hemispherical niche in the wall is used to create very subtle color changing effects. One of the reasons I like this particular installation is because it doesn't immediately gravitate to the highly saturated colors that LEDs are capable of, but rather the designer chose an aesthetic which emphasizes more pastel colors. And I think with LEDs, because you can do something doesn't mean you should do something. This is akin to, I think, the trends that happened in desktop publishing in the early 80s, where people began using fonts and various attributes such as bolding and italicizing fonts. So your memos ended up looking like ransom notes, but you really weren't improving graphical design. You were doing it because you could. And I think the same holds true with lighting as well. The Morimoto restaurant in Philadelphia uses LEDs to light up the partitions between the dining areas. And these various small cubicles use frosted glass as a partition with a linear LED-based light source shining up into it to provide a uniform glow. The control capability of LEDs comes into play here, wherein the color of these partitions is very slowly changing over time. You can't actually see it. It's not perceptible just watching it, but it's over a very long period of time. So you will notice it if you look back many minutes later and wonder why something went from green to magenta. W Hotel has used LEDs in a variety of its installations. And these include diffuse surfaces that are backlit with LEDs. These include various types of fabrics and glass and so forth that are used in a variety of their facilities. This one is in Seoul, Korea. And various lounges and clubs and restaurants are widely using LEDs for a wide variety of applications. We're also starting to see a surge in the use of LEDs for residential applications, and they range from the rather abrupt or maybe not everyone's taste, but this is an Orange County residence which is lit exterior lit with LEDs. And another application which is quite common now, home theaters are being lit with LEDs such that they're combined with the control system such that when you start a movie, the light sequence, the screen comes down, the projector turns on, and you watch your movie. And I think in one of the more striking residential applications, lighting designer took a luminous surface and embedded it in the floor using LEDs to backlight structural laminated glass. So it forms a glowing surface within this residence, which is quite beautiful. The other aspect of lighting that I've seen, I really enjoy a great deal, is seeing the effects of LEDs on art. I believe the artists are not bound by convention, and as a result come up with many, many types of very interesting applications of LEDs that may point the way to new uses for LEDs and embedded surfaces and so forth. This is Traveling Light by artist Peter Freeman out of the United Kingdom. This is an outdoor installation showing an array of LEDs around a column. This is Crown Fountain in Chicago, which is at Millennium Park in Chicago. Beautiful installation by Jaume Plenza, a Basque artist who used LEDs embedded in these monolithic glass block towers, both for the faces that are used. These are pictures of residents of Chicago, and then around the columns themselves. And at night it's quite striking and very beautiful. Another sculpture is the Prow sculpture in New York City at the southwest corner of Central Park at Columbus Circle. The Prow on the Time Warner Center. The various edge-lit pieces within the prow are used and color change over time, and in fact form a clock that, if you're able to interpret the colors correctly, tell you the time. There are also many theatrical applications. I find it ironic that in the early days of LED lighting that lighting designers who often use color are associated with the theater, and when presented with this new light source thought it interesting but too expensive and not bright enough. That certainly has changed over the years, and now we find LEDs throughout theaters and on Broadway everywhere, including large set pieces such as Hairspray shown here, where the dominant set piece in the play is entirely formed of LED systems. Many types of traveling productions, as well as stationary or steady, solid productions that stay in one place, are also using LEDs. In this case, the Nutcracker for the Boston Ballet using LED systems. We also have many applications in interior architectural, and this is probably the greatest growth area, certainly for general illumination. This is a restaurant, the Rustic Kitchen, showing the effects of color temperature change using LEDs within the same setting, where you're able to actually adjust that. So you might have a different lighting scheme for lunch versus dinner, midday versus evening, and this is just one of many ways in which control can be introduced into this. Another retail setting for a shoe store using controllable light, white light and both using both cool color temperature and warm color temperature LEDs to provide you with variable color temperature selections. There are also many architectural applications. One shown here we saw earlier in the energy saving slide, Hard Rock Hotel and Casino. As I mentioned, 1,000-watt metal halide fixtures replaced with LED systems. When designers first saw this, this is really what convinced many that LEDs were here to stay. This is lighting the exterior of a 10 or 11-story building from the ground with LEDs. This is not LEDs at each level on the balconies of the hotel. Takarazuka University of Art and Design in Osaka, Japan used the surfaces of the exterior of the facade with lighting on the inside to create a wonderful color mix. One of the very first LED facade applications was in Chicago at the Goodman Theater, which used wall washing devices and scrims on the interior to create colors for each lighting panel within the facility. In Japan, a facade application as well using individually controllable nodes. When I first saw this, I thought, this is finally Blade Runner come to life. The rather prescient film of the early 80s has really happened in part due to the images shown in that movie have really become real due to LEDs. Harrah's Casino in Atlantic City, showing the different types of facade applications. You can see the many different patterns here. And there are many other types of applications, ranging from bridges, where the LEDs are shown along the bridge deck here. You can see them red on the right-hand side, changing to blue on the left-hand side. And this is very much a worst-case application. Bridges have all sorts of issues with vibration, temperature, humidity, lightning, maintenance, and more. So these are some of the worst possible environments for any type of lighting system, but in fact are well suited for LED systems. Many television sets are migrating to the use of LEDs on the sets themselves. We're starting to see many game shows over the past several years using LEDs in the sets due to the reliability, due to the ability to change colors, due to the ability to last a long time and be reconfigured very easily. This is a cruise ship using LEDs within the large atriums and large venues within the ships. The cruise ship lines love this because the lower energy use and the high reliability is paramount to their operations. This is an installation, La Cittadella in Kawasaki, Japan, which is both a fountain, shown on the left-hand side, and a tower, shown on the right-hand side. There's quite a feature to LEDs. As you can see already, it's been in widespread use for many types of applications, especially color and effects applications today. But I think what it offers us is the chance to reinvent light as a medium. I think artists in particular have looked at light as a new medium, ranging back to Dan Flavin, who actually used fluorescent tubes. You can see that on the left-hand side, to Leo Villarreal, who uses LED tubes on the right-hand side. And we're going to see quite a resurgence, I believe, of light as art due to LEDs, and that will continue to evolve, and LEDs will be integral to that. But LEDs offer a whole new medium, and most new mediums, if we look into radio and television and movies as examples of mediums, they often imitate their predecessors. And lighting is no different. People are trying to shoehorn or force fit LEDs into existing form factors and existing ways of doing lighting. But every new medium needs a time to form its own form and its own vocabulary, and that will take time. LED lighting will do exactly the same thing. But don't think of LED lighting as simply a replacement technology. If you approach it in this way, you're actually weakening its capability. It becomes rather short-sighted because LEDs can do so much more and many different things. I think if we look at the future, there are many easy predictions we can make. The easy predictions are that solid-state sources are changing the face of lighting. All colored light is in transition. Performance will continue to increase. Costs will continue to decrease. We have white LEDs, which are several years behind in the curve, but are also following the same trends. And so we have an enormous opportunity in front of us. These are the easy predictions because this is happening now and we see the trends very clearly. But the hard predictions are, what is a fixture? What is a lamp? A fixture may give way to new forms. We can integrate these devices into structures, into furniture, and all types of systems and devices. The illuminated, in some cases, may become illuminating. Instead of lighting something externally, why not have that device or that system emit light? And what happens when we have a 1,000 lumen source the size of a quarter? It only uses 10 watts of energy, only costs a few dollars. that can completely change the face of lighting. And we just don't understand the impact of that yet. We just can't. And one thing I'd point out here is that the traditional icon that is used to designate a bright idea is that of the Edison lamp. And I can easily imagine a future not too far off where a child will ask their grandparents, "What is this? And what happens when the incandescent source disappears?" Well, we predict the icon will actually outlive the lamp.